New plasma wave discovery above Jupiter's pole reveals astonishing insights. Imagine this. A spacecraft orbiting Jupiter has just uncovered a phenomenon that defies our current understanding of plasma waves. Since its arrival in Jupiter's orbit back in 2016, NASA's Juno spacecraft has been on a mission to demystify the solar system's largest planet. And now, it has stumbled upon something extraordinary, a completely new kind of plasma wave hovering above Jupiter's North Pole. But here's where it gets controversial. This discovery challenges what we thought we knew about plasma behavior in magnetic fields. Let's dive in. In a study published recently in Physical Review Letters, a team of astronomers detailed an unusual pattern of plasma waves detected in Jupiter's magnetosphere. This magnetic bubble acts as a shield, protecting the planet from external radiation. Jupiter's incredibly powerful magnetic field seems to be the mastermind behind this strange dance of plasmas, forcing two distinct types to move in sync and create a unique flow of charged particles and atoms near the poles. Plasma, a superheated, charged gas, plays a crucial role in shaping Jupiter's chaotic atmosphere. The researchers believe that these new observations will not only deepen our understanding of Jupiter's weather patterns, but also shed light on the magnetic properties of distant exoplanets. And this is the part most people miss. The implications for exoplanet research could be enormous. For this study, the researchers focused on the behavior of plasma waves in Jupiter's magnetosphere, which is filled with highly magnetized, low-density plasma. The team, composed of scientists from the University of Minnesota, the University of Iowa, and the Southwest Research Institute in Texas, discovered an unexpected interaction between Alfvén waves and Langmuir waves. These waves represent the movement of plasma's atoms and electrons, respectively. Normally, electrons are much lighter than charged atoms, causing the two wave types to oscillate at different frequencies. However, in Jupiter's magnetosphere, these waves were moving in tandem, prompting the researchers to investigate further. Their findings revealed a never-before-seen type of plasma oscillation near Jupiter's poles. These plasma properties are truly unique, not observed anywhere else in our solar system, said John Leif Jorgensen, a planetary scientist at the Technical University of Denmark, who was not involved in the study. Unlike Earth's auroras, which are triggered by solar storms, Jupiter's auroras are a result of its powerful magnetic field. These auroras are a spectacle of superfast, highly energetic particles, hundreds of times more powerful than Earth's. Understanding these phenomena could be crucial for future missions searching for alien life on exoplanets, according to the study authors. While these conditions do not occur on Earth, they might exist in the polar regions of other giant planets and potentially in strongly magnetized exoplanets or stars, the astronomers noted in their paper. Jupiter is the Rosetta Stone of our solar system, said Scott Bolton, Juno's principal investigator, on NASA's mission page. Juno is our emissary, sent to decipher Jupiter's secrets. Initially, NASA planned for Juno's mission to end in 2017, with the spacecraft intentionally crashing into Jupiter's atmosphere to comply with planetary protection protocols. However, Juno's flight path evolved, and NASA determined that the spacecraft no longer posed a risk to Jupiter's moons. Consequently, the mission was extended. That said, scientists anticipate that by September of this year, Juno's orbit will naturally degrade, and it will meet its end in Jupiter's atmosphere. But don't think this marks the end of Jupiter exploration. The Europa Clipper mission is set to reach Europa, one of Jupiter's moons, in 2030. And even after Juno's demise, scientists will have a treasure trove of data to analyze for years to come. So what do you think? Could this discovery change our understanding of the universe? Share your thoughts in the comments below. Unveiling the new plasma wave, a breakthrough discovery at Jupiter. Astronomers have made a thrilling discovery, a brand new type of plasma wave orbiting Jupiter, as revealed by NASA's Juno spacecraft. This groundbreaking finding introduces a novel phenomenon that has never been seen before in the cosmos, shedding light on the enigmatic behavior of the gas giant's auroral plasmas. Researchers believe that these newly identified waves are crucial to understanding the extraordinary auroras that illuminate Jupiter's poles, thereby enhancing our comprehension of the intricate space environment that envelopes this massive planet. Exploring the new plasma waves. Jupiter, renowned for its formidable magnetic field and vibrant plasma environment, has captivated scientists for years. The planet's auroras, which are stunning light displays encircling its poles, have been the focus of extensive research. While we are accustomed to the auroras on Earth, those on Jupiter are significantly more intense and are shaped by the planet's expansive magnetic and plasma fields. Robert Lysak, a researcher from the University of Minnesota, along with his dedicated team studying auroras, has made a remarkable discovery. They observed that the plasmas located near Jupiter's poles exhibit a completely new type of oscillation. These oscillations, or waves, are unprecedented and indicate that the charged particles and atoms surrounding the fifth planet behave in ways that remain largely mysterious to scientists. The role of Juno in this discovery. NASA's Juno spacecraft, which has been orbiting Jupiter since 2016, has been instrumental in this discovery. Equipped with advanced instruments, Juno has collected invaluable data regarding the planet's magnetic field and its surrounding plasma environment. By analyzing this data, Lysak and his colleagues were able to detect the unusual behavior of the plasma near Jupiter's poles. The research team concentrated on the ultraviolet radiation emitted near the poles, a vital aspect of Jupiter's auroras. They discovered that the plasmas oscillate in a previously unidentified wave pattern. This new type of plasma wave opens exciting avenues for understanding how Jupiter's powerful magnetic field interacts with the plasma that surrounds it. Why this discovery matters. The identification of this new plasma wave is not merely an academic interest. It represents a significant advancement in our understanding of the broader dynamics of space weather. The auroras at Jupiter's poles are among the most powerful displays in our solar system, and deciphering the mechanisms that drive them could yield critical insights into the behavior of other celestial bodies with strong magnetic fields, such as Saturn or Uranus. Furthermore, this discovery enriches our overall understanding of space plasmas, which are essential components of the universe that influence everything from solar-wind interactions to stellar behavior. As Robert Lysak poignantly stated, cutting off the mission when it is getting its best data would be a real tragedy for our field. By investigating Jupiter's plasma waves, scientists can also enhance their understanding of Earth's own magnetic field and auroras, establishing connections between the two planets that were previously unclear. But here's where it gets controversial. Could the insights gained from Jupiter's plasma waves lead to new theories about the nature of magnetic fields across the universe? What do you think? Share your thoughts in the comments below. Uncovering Jupiter's secret. Rare plasma waves above the North Pole, NASA Juno mission. Shocking discovery above Jupiter's North Pole. Scientists uncover a plasma wave pattern never seen before. But here's where it gets controversial. And this is the part most people miss. You might have to rethink everything you thought you knew about magnetospheres. After nearly a decade circling Jupiter and its moons, NASA's Juno probe has swung so close to the giant planet's North Pole that it detected something truly unexpected. A new kind of oscillation in the thin, electrically charged gas, called plasma, that fills Jupiter's magnetic bubble. As Juno's orbit slowly shifted over 9 years, the spacecraft's closest approach crept toward higher latitudes. This precession opened a window onto Jupiter's auroral regions and led to the astonishing observation of waves in the planet's magnetosphere unlike any previously recorded. To appreciate why this is such a big deal, let's break down the basics. Plasma is often called the fourth state of matter. Imagine a gas so hot or energized that atoms split into a mix of free electrons and positively charged ions. Magnetic field lines are invisible lines of force around a planet or star. Charged particles tend to follow these lines like beads on a wire. In textbook plasma physics, electrons slam back and forth along the field lines in collective oscillations dubbed Langmuir waves, at a characteristic frequency called the plasma frequency. Ions, on the other hand, jiggle up and down across the field lines in what are known as Alfvén waves, with a top speed tied to the ion gyro frequency, the rate at which ions circle those magnetic field lines. But Juno's observations didn't fit that tidy picture. The Alfvén-type waves it detected never climbed above the plasma frequency, which in this case lies below the ion gyro frequency. In simpler terms, both wave types hit the same speed limit, and the expected hierarchy of frequencies completely flipped. According to classical theory, Alphane waves should extend up to the ion gyro frequency, and Langmuir waves should remain well above that. Instead, on Jupiter's polar magnetic field lines, both oscillations cap out at the plasma frequency. To explain this odd behavior, University of Minnesota researcher Robert Lysak and his colleagues dove into the math connecting wave frequency with wave number, the number of ripples per unit length, in Jupiter's very strong magnetic field and sparse plasma. They show that at high wave numbers, Alphane waves can morph into Langmuir waves, a conversion triggered by beams of electrons shooting upward from the planet's aurora. These electron streams, with energies ranging from 1,000 electron volts, 1 keV, to 2 million electron volts, 2 MeV, were first spotted by Juno back in 2016. Why does this matter beyond Jupiter? If this mechanism holds up, it adds an entirely new chapter to our models of magnetospheres around not just planets, but also magnetized stars, and even some exoplanets that boast their own magnetic shields. It could refine our predictions of auroral displays, particle acceleration processes, and the way plasmas behave in extreme magnetic environments, insights that may guide future space missions and laboratory experiments. Controversy spotlight. Some experts argue that this wave conversion process is so specific to Jupiter's low-density polar plasma that it won't generalize to other worlds. Others claim it forces a radical rethink of plasma physics across the cosmos. What do you think? Does this finding demand an overhaul of current magnetosphere models, or is it a Jupiter-only curiosity? Share your thoughts below. Are you convinced, curious, or skeptical?